Good day to everyone. Welcome to our next session where we continue our discussion on sequences, mainly sequences of numbers. So we've seen some introduction so far. We are hopefully getting used to the language, getting used to reading and writing some formulas by way of those four basic functions and those four basic sequences and formulas, and just modifying them briefly. Let's look at our next chapter, technically, where we just continue and look at a specific kind of sequence. The topic as a whole is too difficult, too big. So to make it more manageable for us, we want to look at specific things and build on those things. So let's look at exercise 2.1. It's really just an introduction exercise, but it gets the point across and gets the discussion started. Just see if it fits on the screen. Yeah, I can't make it much bigger. The school population for a certain school is predicted to increase by 50 students per year for the next 10 years. If the current enrollment is 700 students, just what is happening? So we have 700 students to start with, and then we increase by 50 every year. Let's see, what is the sequence that we get in exercise? What was this? 2.1. 2.1. So our sequence is 700, and then of course 750, and 800, and 850, and 900. Nothing too difficult, I hope. And we can also explain this pattern by way of a recursive formula. So see how we're building on what we have done before, where in the recursive formula, we have to specify, where do I start? I start with the first term being 700 in this case. And then in words, I'm adding 50 every time. So that means to get a term in some position, could be position 2, could be 3, anything you may be interested in. I have to take the previous term and add 50. Now this isn't new. We can make another example where we've seen this in a previous exercise. The sequence 1, 4, 7, 10, 13. I like to start with that one. The numbers aren't too big, but I do realize that I could have any starting point and any consistent amount that I add every time. So let's look at this one, for example. Here our recursive formula is A1 is 1. We've seen this before. And AN is AN minus 1 plus 3, or n equal to 2, 3, so on. Yes, in words first, but we've seen this before. I add 3 every time. So to get any term, I need to take the previous one and add 3. So it's it's an easier translation because it essentially copies me word for word. So translations like that are easier. But like we said before, it has the downside that I can't really get away from filling in the numbers one at a time to make my sequence longer. I don't have the luxury of jumping ahead. And what if I want to know what is the 10th number in the sequence? without doing them all. What is the 100th number? The 500th number? I can't do them one at a time anymore. So that's the downside of the recursive formula. But first, let's just give a name to these kinds of sequences. You can start with anything, but I'm always adding the same number. So let's look at this one specifically. We call this sequence an arithmetic sequence. Now, in my sort of naming of the sequence, I have to specify the two key aspects that define this sequence, which is the first term. So with first term 1, and then I need to specify what is the number that I add every time. We're going to call that the constant difference. And in this case, it's a 3. But I realized that the first term and the difference, they don't have to be the same every time. The arithmetic sequence just has this property that I add the same thing every time. So in general, I can say, well, what if I have a sequence where I don't want to look at a specific example? I don't know where I'm going to start. I'm going to start with sum A. Then the next time, I'm going to add a number to that. Might be 3, but it doesn't have to be. I don't want to be committing myself to a 3. I'm going to call it D for difference. Then the next term, I'm going to take that and add another D, so I would have add 2 Ds. And then I'm going to add another D to that, because I always add the same thing, 3 Ds, and so on. So the formula in general would be start with some number first, and then to get a term, take the previous one and add this difference. And that would work, of course, for all the upcoming positions. So in general, the first term could be anything. The difference could be anything as long as it's the same, it's constant as I jump. We call that an arithmetic sequence. I guess because it's based on the simplest arithmetic, adding a number. Of course, that number could be negative, and then I would subtract. But addition and subtraction, those are the easier arithmetic operations, rather. Right, so that's an arithmetic sequence. Now, once I identify a sequence, a specific one, as an arithmetic sequence, I might have properties. I know the recursive formula looks like this in general. So if I identify, I have a sequence here. First term is 1. My jump, the number that I add is always the same, 3. I know the recursive formula is going to look like this template with a specific first term A, with a specific difference D, and I can just fill it in. But it still has the drawback that I can't really work with a sequence like this much. The recursive formula is stuck to the beginning, stuck to what I know already, and I can extend this one at a time. I would like to have an explicit formula for this, to be able to have more flexibility to handle more kinds of questions. So that is the goal. So let's say here, I want to have an explicit formula so that I can get away from this downside that comes with the recursive formula. Let me just remember my sequence. And I remember that the explicit formula will rely on the position values only. And in this case, my example is 1, 4, 7, 10, 13, and it continues like this. I want to know what is a formula that gets me the term in any position that just relies on that position value, not on previous terms. Explicit formula. So for that, what helps me is to just make a list here. The position versus the term in that position. For some reason, I don't know why, for some reason making it 2 columns makes things easier for me. You might be different, but it works for me. I don't know why. It makes a huge difference in helping me recognize patterns when I list them underneath each other rather than sideways. I don't know why. So I'll have position 1, 2, 3, 4, 5. That should be enough. And eventually I do want to extend this to a general position, but that happens later. So I'm going to write my terms over here, 1, 4, 7, 10, 13. I'm going to skip the first one because it's usually special, and we'll come back to it. Where does 4 really come from? 4 comes from the first term plus 3, because that was what the pattern that we saw. Where does 7 come from? 7 comes from the previous term plus 3. The recursive formula definitely is the first thing that comes to mind, and it is correct. It's not very user-friendly past writing it down. This 4, however, is the previous term, which has its own expansion, 1 plus 3. And then this 3 is new, right? 10 comes from the previous 7 plus 3. But 7 itself has a more detailed version, 1 plus 3 plus 3. And then I have this extra 3. I'll do one more. 13 comes from the previous 10 plus 3. 10 itself can be expanded as 1 plus 3 plus 3 plus 3. And then I have this extra 3. So let's write them all over here. I now get 1 plus. I'm going to skip that one for a second. Go to 7. I have 1 plus 2 times 3. I use a dot, but you can use a times symbol if you want. I have for 10, 1 plus 3 times 3. For 13, I have 1 plus 4 times 3. I do have to check the first ones, whether they fit this pattern. 1 plus, 1 times 3. And technically, the first term can be written as 1 plus 0 times 3. I just don't add any 3's. So now I can look at a calculation to find these terms and try and see a pattern in that calculation. And I see, well, the 1 is always the same. The fact that I'm adding 3's, that's always the same. It's only this one. The number of 3's that I add, that number is changing. And ultimately, I'm trying to find a link between the position and a way to calculate the term. So now I want to see, okay, well, if I'm in position 1, this changing number is a 0. Position 2, the changing number is a 1. Position 3, it's a 2. Position 4, it's a 3. Position 5, it's a 4. And I notice it's always 1 less than the position I'm in at that stage. So if I'm in general position n, I can say, well, the calculation is always going to be 1 plus a certain number of 3's. How many 3's? 1 less than the position. There is my formula. So writing a table like this, extremely useful to me for some reason. I think having it as a column just helps me let me have space to expand this and pull it apart. Where does this 10 really come from? What makes this 10 a 10? Let's see its detail. And then let's see a pattern in the detail. that links to just the position. And you see here, so here I can now, let's say like this, have an explicit formula. an 1 plus n minus 1 times 3. And that applies for everything from the very beginning. From the first position on, I have a way to calculate the term in the position I'm interested in that just depends on that position value. Now, I prefer to leave it exactly like this and memorize it like this. I don't care to simplify it. Simplification just hides the pieces and where they belong. If you really want to simplify it, go nuts. I will never do it. I don't need to. There's no benefit in doing that. This, notice, this 1 comes from the very beginning, the very first term. Can we still see this at the bottom here? I'm trying to squeeze it in. Yeah. What else comes from the sequence itself? Well, this 3 isn't random. That line was random. This 3 in the formula comes from the number that I add every time. 3, 3, 3, 3. And it becomes a certain number of 3s. So this is the constant difference in my arithmetic sequence. So if I have a general random lines, hold on here, something went wrong. Accidentally opened something I shouldn't have opened. Close. Come on, close. Let's see. Let's see, I had some freezing happening here. Oh, I think everything's on track. So in my specific example, the pieces in the explicit formula comes from the key properties of the sequence. The arithmetic sequence has 2 key properties. The first term and the difference. And those numbers feature in this explicit formula. So now if I go to sort of extend this to what the formula looks like in general without me having a specific example, here we can write this. So this was the recursive formula. Just get rid of these dotted lines a little bit so I have some space. Squeeze in here the explicit formula. If I have an arithmetic sequence with first term A and difference D, then the explicit formula is going to be an, first term, plus n minus 1 times D. And of course, it works for all positions. So now the benefit is that this has now been established in general for any arithmetic sequence. Whether I start with 700 and have a difference of 50, I can write the explicit formula here. Because I identify it as an arithmetic sequence and everything is known about the arithmetic sequence, I therefore know everything about this sequence. And that's the benefit of classifying sequences. And this is our first classification. Everything's worked out for arithmetic sequences. this is an arithmetic sequence, therefore everything's worked out already for me. Explicit formula will be a n first term plus n minus 1 times 50. And now if I go back to the question, where was the question? The very first question. After 10 years, how much do I have? How many students do I have after 10? So that's the 10th term in the sequence. Yes, I could have done it one at a time. Add 50, add 50, add 50, add 50. Okay, I'm 5 in. Do it 5 more times, and I'll get the 10th one over here somewhere. I don't even have space on my page. The benefit of the explicit formula is I don't need to do them all one at a time. I can jump to whatever position I want. If I want the 10th term, I can do that. The 10th term is simply A10. I plug n into the formula because the explicit formula only depends on the position, and I calculate that. I'll take this opportunity to show that we have a calculator in the chat as well. His name is MathBot, and to do a calculation I just have to type 2 equal signs, and I'll just do a simple one like 2 plus 3 just to show you. 2 plus 3. Oops. Maybe I should. 2. Oh, I have shift on for no reason. Things weird. Why is my keyboard so weird? Keeps me on my toes for no reason. There we go. That's better. There we go. And MathBot says 5. Now you might have your own calculator, but if you really want to have some fun with it, you can use a calculator in Discord itself in any chat box in our channel. So let's calculate this. I can't speak and type, so that's why it'll be quiet a little bit maybe sometimes. 700 plus, I'll just say 9 times 50. I know you can do it in your head. I just wanted to demonstrate our calculator so that we see it in the chat as well, and you can verify 1150. And we can then say, well, I know that there will be, if everything continues like this, 1150 students in the school. So it is strongly encouraged that you memorize the explicit formula for the arithmetic sequence, because I don't want to go and derive this and make a table for something that should be straightforward. I don't really memorize the recursive formula because it is a direct translation, word for word, from what I say in words for the pattern. But the explicit formula, I look at a sequence and say, oh, I add the same thing every time, therefore it's this. No, it's not obvious to me. It comes from my analysis by way of a table that this is the formula. So because it's not as direct a translation, it's beneficial for me to just memorize this one. So now if I see any arithmetic sequence, I know exactly any formula and I can use it. So let's see how that goes. Questions at this stage. So we have some stuff here that you can read in the book if you want to. Exercise 2. Actually, let's do 2.4 first. I'm giving you a formula that doesn't look familiar. Sometimes it's explicit, sometimes it's recursive. Who knows? I want to know, does this formula define an arithmetic sequence, yes or no? Now, sometimes I might recognize it, and sometimes I might not, because I memorize my my explicit formula in a very specific way that as soon as someone simplifies it, it might not look familiar to me. But what I can do is just write the first few terms of the sequence. Let's say 5 should be more than sufficient, and then I'll see if it's arithmetic or not. So in the first one, I have a n, 2n squared plus 1. N goes from 1 and so on. I should write that down. 1, 2, so on. So my sequence is therefore 1 squared, which is then the 2 plus 1, so 3. Then position 2 is 2 squared is 4, 8, 9. 3 squared is 9, 18, 19. In position 4, 4 squared is 16, so it's 32, plus 1 is 33. I'm in position 5, so 25, 51. And I can keep going. And now I see, okay, well, I'm adding this, specifically seeing if I not notice a pattern, if it is an arithmetic sequence, which means I have to add or subtract by something, and that something has to be the same every time. And I see it is not the same. So I conclude it is not an arithmetic sequence because it doesn't fit that template. Okay. 2, I have another formula. I don't recognize it, but I can just make a few terms in the sequence and see what kind of sequence it is. My sequence is first position, so 3 times 1 minus 1 is 2. Second position, so 3 times 2 is 6, minus 1 is 5. Third position, 3 times 3 is 9, minus 1 is 8. Fourth position, 12, minus 1 is 11. Fifth position is 15, minus 1 is 14, and so on. And now I see I'm adding 3, I'm adding 3, I'm adding 3. Oh, I'm always adding the same thing. Therefore, this is an arithmetic sequence. But S is so far away, it's super weird. Back here, S, you are a part of this word. Sequence, arithmetic sequence, and then I have to specify what's the properties of this. Sorry, not the properties. I guess properties if you want to say it like that. This is an arithmetic sequence with, I have to say 2 things. First term is a 2, and sometimes we leave the difference because the constant word in constant difference, because arithmetic sequence, the difference is always constant. So we sometimes just say the difference is a 3. Then I can continue and write the formulas if I want to, but oh, it does ask, what is the other type of formula? Well, they were giving me a version of the explicit formula. So the other type of formula is a recursive formula, which has 2 parts. First term, 2. Essentially, I'm just repeating what the sentence says, right? In a way. Using the difference, I can find a term by taking the previous one and adding 3, and that's going to work for the second term, third, fourth, 1. Because I identify it as an arithmetic sequence, everything's known. It's in a way the easiest sequence. Everything is already figured out. Some things I have to just understand. I don't memorize the recursive formula. It's a translation issue. But the explicit formula is something that might be handy to memorize. Next one. See, random line. 3. Yes. The recursive formula I can get by just looking at it, right? Because that's a direct translation. So I don't bother, honestly. The explicit formula, to me personally, is not obvious immediately as the recursive one is. And it therefore has convenience. Skipping the table by just memorizing it is going to save me a little bit of effort because look at this table. I don't want to do this every time. Apparently, I've lost the ability to scroll up and down, but the table's down here. And that's not something I want to do every time. I do that once, see what the explicit formula looks like, see how its pieces come from the sequence, the first terms appearing, the differences appearing, and then I'll just memorize it. Just to save time, it's much more efficient. But I don't want to memorize stuff just because I like memorizing stuff. I don't. I want to minimize it. But when there's a benefit to doing that, then certainly memorize. But there has to be a benefit. Let's see, what was that last one now? Now that one is a recursive formula that's given, and there's not much you can do. The recursive formula is so simple that it is obviously an arithmetic sequence because it says take the previous term and always add the same thing. So obviously I can just look at this recursive formula because the recursive formula of the arithmetic sequence is so simple, they can't really hide what's happening here. But if you want to be even more convinced, we can certainly make the sequence. It's the same sequence. Oh, that's boring. Change it. That's lame. Let's change it. I have the exact same sequence. Let's make it a 4. Doesn't really change much. But it is technically a different sequence. 2, 4, 2, 6, and then a 10, and then a 14, and then an 18, just to have it slightly different at least. And you see here I'm adding 4 every time, right? So this is an arithmetic sequence with C. I have to specify what is the first term. What's a 2? And the difference is obviously a 4. Then they say find the other formula, which is the explicit formula. They gave me the recursive formula, and the explicit formula I now memorized is the first term plus n minus 1 times the difference. This is how I memorize it. Of course, there are different versions of this. Oops. Because you can simplify this one and make it look a little different. I pick one that is the easiest for me to remember where the pieces go, and I don't care to simplify it. That's what I'm going to use. I don't want to make it more difficult for myself. But there is a convenience, right? It's not obvious to me. Look at the sequence. Can you write this down from that sequence? No. I need to remember the template with what piece goes where. It definitely helps. Okay. So this just helps me memorize and get used to the look of the explicit formula. We can now see its benefit by way of exercise 2.2 and 2.3. So exercise 2.2 asks, how many terms are there in that sequence? Copy it down so we can see it. So I don't have a lot of space. Let's make a new page first. Time. Okay, so we're doing exercise 2.2. And I'm given the sequence 1, 5, 9, 13, and then some stuff happens. That pattern continues, and at some point I'm going to hit 125. They want to know, when do I hit 125? Now, of course, I could give this little Timmy, assuming he has the patience, he notices the pattern. Oh, I'm adding 4 every time. Yes, Timmy, good. But how long is it going to take you to get to 125? He has no choice, but do it one at a time and then count until he hits 125 and then count how many numbers he got. That's, of course, completely inefficient. We can exploit the explicit formula because it allows us to jump ahead. So you have to, however, defend why you can use that explicit formula, because this is an arithmetic sequence with first, that is an R and an S. It does not look like it. First term 1, and you can emphasize constant. Has to be constant or it's not arithmetic. Difference is a 4. Because it has these properties, starting somewhere and then adding the same number every single time, it's classified as an arithmetic sequence, and therefore I can use the explicit formula, which has this template form, just filling in this specific first term, this specific difference. 2, 3, all positions will work for that term, for that formula. So now our question becomes, let's say here, what is the position? I'm rephrasing the question. What is the position of term 125? Some point in the sequence, at some point, I'll get a term that has a number 125. If I know the position of that term, then I would know how many terms there are up to that point, because the position counts them perfectly. 1, 2, 3, 4. What's this one? But that position is the only unknown in the right-hand side of this formula. So term 125, I can set my general name for the term as 125, and then find what is the n, what is the position that corresponds to it. So plug in 125 into our formula, which then becomes an equation, I suppose. And now we just have to figure out what is the value of n so that this equation is true. Now, yes, if you're coming from 142, you should know how to do this. If you don't, well, we still have to have math 11. I think that's the prerequisite. So solving equations like this shouldn't be a problem one way or another. I like to just swap things around. I'm going to do it in a lot of detail, depending on your comfort level. Of course, you can scale this back and show fewer steps, but just in case, right? I don't know who is listening right now and how well you remember these things. I like the side with my variable on the left. So I'll subtract 1 on both sides to get n minus 1 times 4 equal to 124. Then I'm going to divide by 4 every time, and maybe I feel, ooh, MathBot, I need your help. I don't know in my head what that is. Maybe you do. Doesn't matter. Either way, just make sure you find the right number. 24 divided by 4. Random line, and MathBot says it's 31. And then I'll add 1 on both sides to get n equal to 32. So that means, this means that 125 occurs, let's see, in position 32. So the sequence has 32 terms. Don't be afraid to write words and explain what you're doing. You don't have to show this much detail. It's totally up to you, though. It wasn't that much. Let me zoom out a little bit. See if we can see the whole thing at once. Explain what you are doing, especially going into teaching. You have to be an effective explainer, so to speak. And it starts now. It starts with good habits. Whenever you have to figure out a problem, whether it's just for yourself, whether it's for me on a test, it doesn't matter. Get into the habit of using words. Explain your thinking. There's time for it. The tests, none of them are long. Ask people in 142. I don't think they were overly long. You had the time to write out words and explain what you're thinking. And anyone who reads it, whether it's me grading it, whether it's you months from now reviewing for the final exam, whoever reads this, it's just so much easier if you use words and explain yourself. Get into those good habits, because those good habits translate to your teaching and you automatically explain things much more clearly. You can't tell little Timmy, it's 32 terms, Timmy. Why don't you see this? What's wrong with you? No, you have to systematically explain how you get to 32. So this is a good demonstration of the explicit formula, where the recursive formula is kind of useless because it doesn't allow me to jump ahead. And for a question like this, which has some space, I don't want to write 32 terms. It's inefficient. The explicit formula, which is essentially capturing the essence of the same sequence, but it's much more effective for certain kinds of questions. Any thoughts or questions about all that? As I might. The arithmetic sequence is in many ways the simplest one we can really sort of set up and do in this way, with two versions of formulas and questions that are a little bit more interesting. Let's step it up a notch and go to exercise 2.3. So there are multiple questions within this question, but essentially it all comes down to find the sequence. I'm thinking of an arithmetic sequence having 10th term 32 and 23rd term 71. Can I figure out what the sequence is and find the 100th term or whatever else I need to do? If I can figure out the sequence, then they can ask me any follow-up question and I can answer it. So it's irrelevant what their follow-up question is. The key is I have an arithmetic sequence. So let's map out what we have so far. We are going to start in position 1 and 2, but they only tell me something about position 10. It's not really very convenient. Then, of course, there's the position 11, which I don't know, and then it keeps going. And then it gets to position 23, they tell me something again, and of course then it keeps going, and eventually I want to know the 100th position randomly. But if I can figure out the whole sequence, then I know with the explicit formula, I can just plug in any position value and find it. So really, even if they ask what is the 100th term, I just need to figure out the sequence, find the explicit formula, and then I can answer that very quickly. Sorry, I missed your question here maybe a little bit. No, only 1 minute ago. Explicit goes with arithmetic sequence. Don't feel bad for having a tough time. It's a new language, and it comes with any language learning struggles. It's no different. Uh, the explicit formula and the recursive formula is for any sequence, but for an arithmetic sequence, they look a certain way, always. So there's a template, if you will, that is attached to this type of sequence. If I have another random sequence, it might have a recursive and an explicit formula of its own, but it won't look like this. It would look weird, different. It's attached to whatever sequence and whatever properties that sequence has. If we talk about arithmetic sequences, we try and keep it simple, where we are adding this or subtracting, fair enough, the same number every single time. When I'm looking at a sequence like that, I give it a name. It's called an arithmetic sequence. It has a specific number that I'm adding every time. That number features in the formulas, and the formulas look a certain way. But change the sequence, and the recursive and explicit formulas change. They're still there, but they're going to look different. So for this kind of sequence, they look this way. So if I identify a sequence, or I'm told, this one, I identify a sequence as an arithmetic sequence, therefore I know what its explicit formula looks like. Or I'm told it's an arithmetic sequence, therefore I know it's given, it's arithmetic, it's being told to me. Therefore I know there's a first term. Now I don't know what it is. I'm going to call it A. And there's a difference that's constant, and I'm going to call it D. This specific formula, explicit formula, all sequences have an explicit formula, but they don't look the same. Some are complicated, some are easy. This one is fairly easy. Whatever the first term is, it's going to go there. N minus 1 always goes there. Whatever the difference is, it's going to go there. Now my goal is just to find those A and D values. But for an arithmetic sequence, it's always going to look like this. Now the information here is trying to make it difficult for me. So what I want to find is the D first. By looking at the steps I take from 32 to 71. So from position 10 to 11, I'm adding a D. From position 11 to 12, I'm adding another D. So I've added 2 Ds. So 1 D, 2 Ds. The next one, I'll add another D because it's arithmetic. It's always the same. So for position 13, I'm going to have 3 Ds. How many Ds am I going to add all the way to 71? Well, 71 is in position 23. 11, I add 1 D. To get to 12, I add 2 Ds. 13, I get 3 Ds. So it's the position minus 10 because I started in 10. So 23 minus 10 is 13. So I'll add 13 Ds. By just looking at or you can simply count them as well. The gap isn't that big. So this is sort of a side note. We're not ready for this yet. I'll squeeze it in here. So from 32 to 71, I know that 32 plus 13 steps of size D is going to get me to 71. I can therefore calculate D by subtracting 32 on both sides. I know I'm running out of time, unfortunately, but I need to finish this. I have 13D 71 minus 32, 39. And then D is 3. So now I know D is 3. And now I can go from a certain number of D steps to 32 every time it's the same step, right? But I already have D, so this is now 3's. And I can find A. I have to quickly finish it. I don't have a choice. We don't want to break it up here. It's Friday as well. We'll forget. So now from A to 32, we can say, well, A plus how many steps of D is going to get me to the 10th step. Well, I add 1D to get to position 2. To get to position 3, I add another D, so it's 2 Ds. So the number of Ds I add is 1 less than the position. 3 gets me 2 Ds, 4 will get me 3 Ds, 10 will get me 9 Ds. But I know D is 3. So this means A plus 3 times 9 is 27 equals 32. I know I have to go a little fast now, sorry. So A is 5. A is 5. So now I know the explicit formula. A is 5 and D is 3. And I can literally answer anything they want. If they want the 100th position, that's easy to do. 100th position, or the 100th term rather, sorry, not position, is A 100. Plug in 100 in my explicit formula. 100, whoopsie, minus 1 times 3, and I get something that MathBot can quickly find for us. 5 plus 99 times 3, and we get 302. So I apologize that was fast. We can certainly repeat it in any Q&A session and have many more discussions about this. How do we feel about that? Unfortunately, we ran out of time, and we can definitely repeat it. Remember, we have a Q&A session Sunday morning that you can attend as well, or you can send me an email if you have any questions that you don't want to wait for. If you want me to check anything, just let me know. These things take time, and we had to squeeze it in there a little bit. Are there any questions that you'd like to share at this stage before we end the session here for now? All right then, review. Remember, watch the video again, watch bits of it again if you need to. It'll be backed up to YouTube by tonight somewhere, and let me know how it goes. Until then, thanks.